If we consider a conventional multi-channel DMA, this is where we would have a number of DMA masters that would sit on an on-chip bus, such as AHB, and they would be arbitrated for. Each would get a turn at reading or writing from the host system via the PCI Express core. Now, obviously, an interconnect like AHB is not desirable when used with PCI Express, and that is because it does not provide full duplex transfer. Now, obviously, you could segment the AHB into multiple segments, but it's still not an ideal bus for this type of application. Now, a more optimized approach for PCI Express is to have two raw DMA engines, an upstream engine and a downstream engine. There's no use in having more engines, more DMA circuitry than that, because only one can be live at a time, and therefore you can have command FIFOs that are going to feed those DMAs and just keep reusing them for different input and output streams. So feeding the command FIFO, you're going to have a scatter-gather engine. The scatter-gather list could live on chip, or it could be off chip and pulled out of host address space. Now, this is a scatter-gather controller example that we have implemented. And so it's similar to the previous drawing, here with a little more detail in the scatter-gather engine. So here we have a way of monitoring the FIFO status. So these would be watermarks from the FIFO. And that is used with a descriptor RAM, which contains instructions. So effectively, this is a little micro-coded engine. Instructions get read, and in the case of a jump instruction, these external conditions control the branch instruction. And then you have registers for initiating DMA. You have a pointer, which is effectively a program pointer, RA, RB, which are for indexing. And then you have a semaphore mechanism via these event registers, which can be used to create interrupts to the host processor. So if you look at the scatter-gather list, it consists of a transfer control value. This is where you specify the transfer count, the direction, whether it's upstream or downstream, and a stream ID, which identifies which FIFO stream that's associated with. And then you have an address high and an address low that forms a 64-bit memory address in the host space. So that address, in the case of an upstream DMA, would be for write cycles, and in the case of downstream would be for reads. The instruction set of the scatter-gather engine is very simple and can be implemented in FPGA with fairly minimal logic. This includes load, store, and add the system address. So this is how you manipulate the 64-bit system address. There's a load transfer control instruction. This is what actually initiates DMA transfer upstream or downstream. And then you have a load, store, and add the RA, RB registers. So this is used to manipulate indexing and counters. There's also the conditional jump, which allows you to make decisions based on status from the FIFOs in the application layer. There's also an event assertion, and this is the semaphore mechanism for communication between the host processor and this little microcode engine. This diagram is a simple scenario of how you would use the microcode engine. It's a simple polling loop, effectively. So here you are making a decision about channel 0 if it needs servicing, so this would be in the case of a watermark event, and if so, then you would initiate DMA transfer. And you would just simply have a loop of these servicing requests. Now I'm going to shift focus to how root complexes behave, because in order to design an endpoint, we need to understand how typical root complexes will operate. First of all, most systems out there, most motherboards, for example, PC chipsets, have a maximum payload of 128 bytes. Some systems, for example, server-class chipsets and newer desktop systems, may have 256. We have seen some at PlugFest that have 512. But the spec will allow for up to 4 kilobytes. Maximum read request size supported. The typical is 512 bytes, but the spec allows up to 4K. Typical read completion packet size. Now, since most systems out there are cache line based, that is, they use a cache line fetching mechanism, this results in a 64-byte cache line packets. So if you start a transfer from an odd boundary, then it will break at a cache line boundary. So some root complex chipsets provide read combining feature. That allows opportunistically the capability to combine 64-byte cache line packets into contiguous blocks that are larger than 64 bytes. The spec allows read completion packet sizes of up to 4 kilobytes, but you'll never see this happen. Virtual channels is another one of those advanced features that PCI Express provides. However, very few chipsets or switches provide more than the default virtual channel 0. The spec allows for up to 8 hardware virtual channels, but again, you will pretty much never see this in real life. One of the trade-offs that you need to make in developing a PCI Express endpoint device is how many outstanding reads you're going to support. So we did an experiment here with about 4 different systems. These are different CPUs, different chipsets. And here we've plotted the results. This is number of outstanding reads versus the throughput. So you can see that when your endpoint supports a single outstanding, then we're getting somewhere between 200 to 250 megabytes per second. That's on a PCI Express Gen 1 by 4 link. If you increase that to 2 outstanding, you can see that those numbers pretty much double. If we go to 3, we get significantly improved results, but it's still not, here we're starting to reach the point of diminishing returns, and at 4 outstanding reads, there's not too much of an increase in performance compared to 3 outstanding. So therefore, 3 or 4 outstanding reads is usually a good amount to support, and having more than that really isn't going to buy you too much.